Yes. Good evening, one and all. So today we are going to discuss the mechanism and theories of fatigue failure in material technology. So before going to that, let me introduce myself. So I am Kakarla Krishna Kishore, professor in mechanical engineering. So as a metallurgist and as a experienced person in the various experiments I have done in materials, so I would like to express some of the various theories of failure. So regarding all those things we will discuss in this session. So let me discuss the mechanism and theories of fatigue failure. So before going to understand the mechanism and theories of fatigue failure, first of all, let me discuss first of all what is fatigue. Here, what is the fatigue failure? Try to observe the words here. Whatever the fatigue failure that you are understand, fatigue means it is a repeated stress. It is a repeated stress. Invariably, fatigue failure begins as irregularities. Here, whatever the fatigue failure that appears on the material, so that started with irregularities on the surface of metals and which acts as a stress riser. So that means whenever some irregularities you are observing on the surface, so those will observe as stress risers. That means those whatever the surface of metal, that is whatever the irregularities that are appeared on the surface of metals, which acts as stress risers and at points of stress or stress concentrations. So that means wherever the stress concentration is existed, the fatigue is going to be generated. So we have to concentrate in the design itself whether the stress concentrations are existed or not in the particular material, maybe on the surface, maybe at some other side of the surface, maybe at some depth. So you have to take care of the design, that is the design stage itself, so that these failures, that is fatigue failure, may not be observed in the particular material. So if you want to avoid these fatigue failure, we must have some thorough knowledge regarding fatigue failures and what do you mean by the mechanism, what is the background of this mechanism and what is happening when the fatigue failure is observed by the material. So and what are the various theories which supports the fatigue failures. If you able to understand all these fatigue failures, automatically you can try to avoid these fatigue failures in the materials, or whatever the materials that you are going to produce in the industry. So this is very important topic in the industry, that is not only in the exam point of view regarding industries. So they have to remove all the fatigue stresses, all whatever the residual stresses which are produced during the production. If you are unable to reduce the stresses, that is residual stresses which are produced in the material, automatically after some time, maybe after one day, maybe after 6 months, the material will get crack. It may be fatigue crack or creep cap. You have to understand which crack is going to be observed in the material. So to understand the cracks which are going to observed in the material, you must have thorough knowledge in one of the cracks which are very rarely or which are frequently observed in the material. Sometimes if you are unable to avoid, so definitely this fatigue failure is going to be observed in any material. Now let me discuss with the definition here. See, I already said that you are observing on the screen the stress risers. The stress risers may be existed and which causes the fatigue failure and the stress concentration. So that means you have to observe the areas at which area the stress concentration is existed. So now let me discuss with the help of definition here. First of all, try to observe the figure that you are observing here. This is the figure. So continuously it is having, that is load is applied on the material. Because of all these loads, what happens after some times, the fatigue will be observed by the material. So due to the fatigue, the material is automatically deformed. So please observe the definition first. The fatigue failure. What do you mean by fatigue failure? Fatigue failure is defined as the tendency of a material to fracture. So that means it is the nature of the material whenever the load is applied. So whether you have to take care of the material load, whether the load is applied frequently or at some frequent intervals of time or at the different stages. So what is the frequency of the load? That is very, very important. How much load is applied on the material, at what frequency the material load is applied. All these are very, very important to study the cracks. Here, the fatigue failure, that means the fracture which is observed during the fatigue failure means the fracture by means of progressive. Please observe the word here, the progressive brittle cracking. It is due to the progressive means continuous brittle cracking. So you can observe in the image, so the deformation, the crack, the complete deformation, the permanent deformation of this particular shaft is observed due to the progressive brittle cracking under repeated. This word is very, very important to understand the fatigue failure. Repeated alternating or cyclic stresses. Cyclic stresses means the stresses which are going to be repeated of an intensity considerably below the normal strength. So you see, the strength may not be a higher strength. The strength may not be, or the load may not be the higher load. It may be a normal load. It may be a small load. But if it is observed on the material for a particular period of time and at frequent intervals of time, that is very, very important. At what time, at what frequency the material is observed these particular loads. If the material is observing the continuous loads, that means progressive loads, automatically you can say that after some time this material is going to be deformed. So that is very, very important to understand this fatigue failure. So here, what is the mechanism behind this? See, if you want to understand the fatigue failure, so we have discussed the definition of fatigue failure. Now, let me discuss the mechanism behind this fatigue failure. Here, in general, whatever the fatigue failure that you are saying, it is initiating from stress concentration. So that means what you have to observe, the stress concentration area. Whatever the stress concentration areas are observed in the material. So what we can do? See, we cannot avoid stress concentrations. We can reduce stress concentration. I repeat this particular sentence because this sentence is important to understand the fatigue failure mechanism. I repeat, whatever the fatigue failures that you are observing in the material, if you want to avoid, if you want to reduce the fatigue failure mechanisms, you cannot completely avoid the fatigue failure, but you can reduce the fatigue failure. Here, by avoiding, that means wherever the stress concentration areas are existed in the material, you have to avoid those stress concentration areas. So that means which are the starting points of the fatigue failure. So whenever the stress concentration areas are observed in the material, automatically the fatigue failure will start. That means the fatigue crack will start from those points at which the stress concentration is existed. See, so many salient features are available. Usually, what are the components that are intentionally over designed? So that means what is important here? The design is important. When you are designing any material, and you have to take care of the stress concentrations must be avoided. So that means here designed to deal with stresses several times greater than what they would be subjected to in service as safety margin. So that means if you want to be the material, that means whatever the material that you are going to produce, if you want to be safe material, so that means the material is not going to get any crack, maybe in near future, maybe after some time, at least it has to be in service for a particular period of time. If you want to be like this, that means if your material must have this type of strength, you have to avoid the fatigue crack. So that means you have to avoid the fatigue failure that is in the material. So how to avoid fatigue failure? If you know the fatigue failure, how it is happened, why it is happened, and what are the various reasons which causes the fatigue cracks and fatigue failure mechanism. So we are going to discuss all these things in this session. The theory behind this and the causes behind this particular fatigue failure. Here, please observe the images here. You are observing two images. One image is having the sharp corner and the other image is having the smooth corner here. So which one you are going to prefer? whether the sharp corner or the smooth corner. Smooth corner means the same particular design, the same design is modified with fillet here. The corner is modified as a fillet form. Here this is abrupt change in shape. Here the smoother change. Which one is required? If you provide abrupt changes in your design, that will lead to a bigger problem in your design. That means for your product, you are not supposed to give the abrupt change. What will happen if you provide abrupt change? You can observe the word here. The stress flow lines crowd high stress concentration. Here, automatically, if you provide abrupt change, automatically the high stress concentration will be observed. If you provide smoother area, please observe this circle in which you can observe here, because of this smoother change, the flow lines are less crowded. Here the flow lines are overcrowded. Here the flow lines are less crowded. That is the main change between abrupt change design and the smoother change design in the material. So that means whenever you want to design some product, maybe casting, maybe forging or whatever, you have to take care of these changes. That means design considerations. If you want to avoid these fatigue limits, that is fatigue cracks or fatigue failures, you have to avoid the abrupt changes in the design. And these sharp corners can be filled with the fillets. That means this design can be modified with fillets like this, so that you can avoid the various fatigue failures that are observed in the material. So what is the mechanism behind this? See, we are saying that fatigue is going to be observed. The fatigue crack is going to be observed. So what is the exact mechanism? What are the various mechanisms? Before going to understand the theory behind this, what is the mechanism of the fatigue? So let me discuss the mechanism here. So in general, the basic mechanism in fatigue is slip. So that means the background of the mechanism. Why the fatigue is happened? Why this failure is happened? Why this fatigue failure is observed by the material? Because of the slip. See, if the slip is happened in the material, that means if the slip bands are observed in the material, automatically we can say that some deformation is going to be existed. Some crystals, whatever the crystals that you have taken in stressed piece, you can say that it is a stressed piece. That means load is applied on the material. Stressed piece of a metal reach their limit of elastic action sooner than others owing to their unfavorable orientation. So which permits slip to occur. So that means whenever the slip is observed in the material, so it indicates the deformation is going to be observed. The fatigue crack is going to be observed. What you have to do here? The slip. We cannot avoid slip. I repeat, we cannot avoid slip. We can reduce the slip. So we have to take care of the measurements and we have to take care of the design considerations so that the slip can be avoided. So that means the entire the mechanism why this fatigue is happened in the material, because of the slip is happened in the material. So now let me discuss the stage wise the various stages in the mechanism. The first one is the first of all the crack nucleation. So that means the crack is going to start in the mechanism or in the material. After that the crack is going to grow. So this is the second stage of the fatigue failure. The third stage is ultimate failure. Please observe the three words here: the crack nucleation, the crack growth, ultimate failure. So these are the three different stages in which with which we can say that the mechanism, the failure is going to be observed in the material. The first one is crack nucleation. Crack nucleation means the crack is going to start. See the material here, that is the analysis here which I have done on some particular material. The ANSYS here, with the help of ANSYS software, we have done a crack analysis here. You can observe this is the position at which the crack nucleation starts. That means whatever the fatigue failure that you are saying, the fatigue failure begins with the formation of a small crack only. It will not start with a bigger crack. It will start with a small crack only. The small crack generally at some point on the external surface. So in general, whatever the crack nucleation that we are saying that, so that crack nucleation will start at which the surface may be existed. In general, the crack will start. So in 90% of the cases, this will happen. In 90% of the materials, the crack will nucleated. That means the crack will start at surfaces. This is the first stage of the crack after repeated loads. The second stage is once the crack, please observe the shaft here. Please observe the shaft. The crack is going to grow. This is the second stage of the material. Once the crack is initiated, that is crack is nucleated in the material, the crack is going to grow in the material. That means the crack formed on the surface. It then develops slowly into the material in the direction roughly, in general I am saying, roughly perpendicular to the main tensile axis. See, if it is a shaft, assume that it is a shaft. So it is analyzed in the ANSYS software and assume that the tensile load is applied here in this direction. One is in this direction, another one is in this direction. Then when the tensile load is applied on the material, in what direction the crack is going to be observed? See, the crack is going to observe in the perpendicular direction to the tensile axis. If the tensile axis is in this direction, the crack is going to be observed in the perpendicular direction. So you can see the crack growth clearly in this particular shaft image, which is perpendicular in direction and the tensile. If you assume the tensile axis direction is in this direction. Now this is the second stage of the material, that is the crack growth, or we can say that the fatigue failure second stage. Now the third stage is ultimate failure. Ultimate failure means in this failure mechanism, the third one, the fatigue crack front advances. That means automatically when the second stage is observed, then it leads to the third stage. When it leads to the third stage, a small amount during each stress cycle. That means the crack is going to be accumulated. So a small crack is started and it is accumulated, it is grown and it is accumulated, and in each increment of advances, automatically the crack is going to be a bigger and bigger. When the crack is going to be a bigger and bigger, the ripple lines will radiate from the origin fractures as a series of approximately concentric arcs. So that means a series of arcs will be generated due to the ultimate, that is in the third stage. Whatever the ripples that are going to generate, these individual ripples, that means circular ripples, are visible only by very high profile, that is high powered, the metallographic method. So we cannot see all the ripples which are generated at the stage of ultimate failure stage. So but we can observe under the microscope or under the high powered microscopic methods. With the help of naked eye, we cannot see the ripples generated in the ultimate failure stage here. See here, see the image. When you are giving the tensile load in this direction, here the crack is started. You can observe here, you can observe clearly the crack is started and the crack is grown and it leads to the ultimate failure. That means the three stages of the theory, that is theory says that, theory of fatigue failure says that, first one, the crack will start, that is nucleate, then after that grow, after that it will failure. That means it leads to failure. Now let me discuss some of the points which are developed when the stress rises, when the stress concentration is existed, or the fatigue failures are existed due to the localized stress concentrations. Please observe here why these particular stress rises, that means stress concentrations are existed in the material. So why this is happened? Why these stress concentrations are happened? You can observe here the abrupt changes in cross section. This is the first reason why the stress, that is localized stress, is happened. abrupt changes, base of surface scratches, root of a screw thread, edge of small inclusion of foreign substances, and minute blowhole. You can see here, these are the various changes or various causes which are important to understand the localized stress. Now, see here, abrupt changes in cross section. You can see clearly which one is good, which one is the poor design. Suppose if you provide the stress, that is a sharp corner in your design, what will happen? If you provide these type of things, what will happen? Whether it is a good design or not. If you provide this, whether it is a good or not. Whether it is, if you provide this, if it is a good or not. See, in all these designs, this would be a better design compared to the remaining changes in cross section. So that means the changes in cross section, whenever the cross section is going to change, you have to take care of the shape. You have to take care of the abrupt change. So that means a smoother design. A smoother change is required to avoid the fatigue concentration or the stress concentration. You can see clearly here why it is happened. The second reason, the next reason is these are the base of surface scratches. If you are unable to avoid these scratches, automatically after some times it leads to cracks. So that means the surface scratches also leads to cracks after some time. So you have to avoid these scratches also. And now let me discuss the theories. Up to now we have discussed the mechanism of fatigue failure. So three stages, we have discussed that three stages are existed: crack nucleation, that is the first stage; crack growth, that is the second stage; and the third stage is the ultimate failure. So these are the three stages which are existed behind, that is the mechanism of fatigue failure. Now let me discuss the theories of fatigue failure. So what is the theory? What are the theories of various theories? What they are saying? So please observe, so many theories are giving the information regarding fatigue failure. Now let me discuss the few important theories of fatigue failure. So many theories are available. Here the one theory which says about fatigue failure is Rong's theory, and the next one is fatigue limit theory, next one is Wood's theory, the next one is dislocation movement theory. So these are the four different theories. See, Rong's theory or fatigue limit theory or Wood's or dislocation movement. So all these theories are saying some salient features about fatigue failure. So they are saying that these theories says that how the fatigue failure is going to be observed in their perception. That means the different scientists observe the various reasons and they understand why the fatigue failure is observed in the material, how the fatigue failure is observed in the material. So if the fatigue failure is observed in the material, how we can avoid this fatigue failure? See, without understanding the theories of fatigue failure, without understanding the background theory of fatigue failure, you cannot understand or you cannot reduce the fatigue failure. So let me discuss one by one. The first one is which says that Rong's theory. First observe the sentence here. According to this theory, the metal is considered to contain small, weak regions along which the slip occurs easily. Observe the sentence carefully, what it says. I already said that the slip causes, that is what are the slip, is the basic reason why the slip, why the deformation is observed, why the crack is observed in the material. Slip is the main reason. So if you able to identify when the slip is going to be absorbed in the material, how the slip is going to be absorbed in the material, if you able to avoid the slips, automatically you can avoid the cracks. It may be due to fatigue, it may be due to creep, or whatever the reason here, whatever the different cracks, whatever the different fatigue failures or different creep cracks, you can avoid by understanding and by changing some design consideration, by doing some modifications, maybe in manufacturing procedure, maybe in design procedure, whatever the procedures you can follow, by doing some minor modifications, you can change, you can reduce these fatigue failures or any other failures which are observed in the material. I cannot say that the failures can be avoided completely. So this is completely a wrong statement if I say like this. We cannot say that we can reduce the material failures. No, we can reduce at least up to some percentage. I cannot say that 100% reduction is possible. 100% crack free material I can provide to you. No, it is not possible for any industry. At least some minor cracks may be existed or maybe at the initial stage, may be generated after some time, maybe after 6 months. Sometimes if the material resists, maybe after 1 year, maybe after 2 years, the material, that means the crack will be generated maybe on the surface, maybe at the depth of the surface on the material. So you have to take care of all these things and you have to make a material so that at least you can avoid up to some time. That means you can avoid the crack at least up to some time. Now, so in this regard, let me discuss the first theory which says the slip is behind all these particular deformations. So that means behind this fatigue failure, what it says, please observe here. According to this theory, the metal is considered to contain small weak regions along which the slip occurs easily. So that means if the weak regions are existed, if the small regions are existed in the material, automatically the slip will generate. It is very easy for slip band to generate slips. Automatically when the slip bands moved, when the load is applied, the slip wants to come out from the material, automatically the generation of crack may be existed. You can observe here. So this is the image, microstructural image under microscope. If you observe here, this is a inclusion. So sometimes inclusion it is saying. So that means a crack is initiated at the inner side of the material. Anyway, we cannot see this particular crack with the help of naked eye. So here, why this inclusion may be generated? See, this inclusion is generated maybe because of it is a weak region, the metal. That means what are the metal that you are taken, that you have produced, that metal also contains inclusions. Inclusions means sometimes we can say that impurities. Impurities means so many definitions are there. All the time you cannot say that impurities means it is a waste material. No. Sometimes it is a foreign materials also. The second material may act as a impurity. Sometimes in rare cases. See what are the impurities which are existed in the material. If it is existed, at what percentage the impurities are existed. If you want to calculate, you have to calculate the impurities which are existed in the material. If you are unable to identify the impurity percentage, then automatically you cannot say that how much percentage of damage is going to be absorbed for a particular material. You can see the sentence here. The metal also contains inclusions, means impurities, which act as notches. So that means how the crack is going to be initiated. If any notch, if any sharp corner is existed in the material, automatically the impurity, that means the crack is going to be generated. Here, please observe the image here. This image is having inclusion impurity, the weak region. This weak region is having and acts as a notch and cause stress concentration. Please observe here. around this inclusion, automatically the stress is going to be generated and the stress will increase. When the stress increases automatically, the crack is going to get and the crack initiated and the grow, and after that ultimate failure may be observed. And what this says, that is what this Rong's theory says. These regions, what are the regions that you have seen? These are treated as a plastic regions in elastic matrix, and these experience increase in stress even when the repeated applied stress is constant. Here, please try to understand this particular point here. Even though the repeated applied stress is constant, the stress is going to be increased in the plus, that is the plastic region. Whatever the stress that is going to be increases causes plastic strain. That means if the stress increases in the plastic region, the plastic strain is going to increase in the weak region. That means here it cannot do anything if the material is strong. If the material is having a complete strengthened material, the strong regions, then it cannot do. So nothing to do with the strong region, nothing to do with the maximum hardness region. But wherever the material is having the weak regions, automatically the stress is going to attack. The stress concentrated in the weak regions, automatically what will happen? It leads to the crack initiation, and the crack regions are going to generate. And the plastic strain, due to the plastic strain, whatever the plastic strain is generated, if it increases, automatically the stress will be increases in the specimen. You can observe here, in general, this is the graph, so which explains the stress versus strain. Suppose if it is a brittle material, it is a different graph. If it is a ductile material, it is a different graph. Here, for any material up to some region, the stress is directly related to, that is strain, and after that this is the plastic region in which we have to take care of. So in this region only the entire problem, the entire damage is going to be observed for a material in the plastic region only. This region is represented as a plastic strain. If it is under elastic deformation, then there is no problem for a material. If it passes the elastic deformation, you can observe here the various slip bands. These are the slip bands here. That means it wants to come out as a slip bands. Then automatically the cracks will be observed on the surface of the material. Rong's theory says so many salient features. Here, this particular plastic strain in the weak region exceeds. If it exceeds whatever the weak regions that we are saying, that if it exceeds beyond a certain value, the crack is formed, and this process is going to repeat it again and again until the large crack is formed. So this is all about Rong's theory. So that means crack is initiated in the plastic strain region, which concentrated on the weak regions, and the process is going to be repeated again and again until the large crack is going to be formed. Now see the other theory, the second theory. Please observe the name of the theory first, fatigue limit theory. We have discussed fatigue. That means repeated load is observed on the material, or a crack is observed. If a crack is observed due to the repeated loads at frequent intervals of time, that crack can be represented as a fatigue crack. I repeat, that crack can be represented as a fatigue crack. But for every crack, for every loads, for every particular, say, crack initiation, there exists a limit. The material is having some limit. The fatigue crack is having some limit. The load cannot withstand. So the material cannot withstand for a particular load. that means it can withstand a load up to some extent, but after that it cannot withstand. That means you have to draw a graph so that what is the fatigue limit of each and every material. So let me explain this. What is the fatigue limit theory says about this particular mechanism and theories of fatigue failure. Let me discuss. According to this theory, the localized strain aging affects the fatigue properties to a large extent. First, observe the sentence. This theory, the localized strain aging effects, that means whatever the strain is going to form, aging effects means due to the time. After some time passes, this will affect the fatigue properties. So that means how much time you have applied the load on the material. That is very, very important. At what frequent intervals of time you have applied load on the material. Along with that, how much load is applied on the material. Along with that, at what frequent intervals of time you have applied. That is also very, very important in understanding fatigue theory or fatigue failure, fatigue crack here. The properties of a large extent. So that means the aging effect, the localized strain aging effects, the fatigue properties to a large extent. Some metals. See, we cannot say that all materials are having the fatigue limit. Some metals have well-defined fatigue limit. So that means if people are going to do some experimentation, people are going to utilize that material as an end product, we can say that how much load can be applied on this material. That is very, very important information for any material. If you are not aware of the load, suppose take the example of the bridge. If you are running so many vehicles are running on the bridge, if you are not aware of the load which can withstand by the bridge, automatically after some times, if you are keeping the maximum load or the huge load, or we can say that overloaded, if the bridge is overloaded, automatically the bridge may collapse, or if it is not collapsed, maybe the crack may be initiated due to those overloads. So what will happen? After the crack is initiated, maybe after some time the cracks will grow, and that leads to the ultimate failure of the bridge. That is the bigger disadvantage of the fatigue failure if you are unable to identify the fatigue failure. So that's why you must have the complete data, how much load can withstand by the material. That is fatigue limit. How much load is absorbed by the material without having any crack. Sometimes information may not be available. All the materials, I cannot say that for all the materials information is available. This much of fatigue limit is available. No. Suppose if you have introduced a new material, so you have to take care of the fatigue limit. You have to calculate by doing some experimentation, by doing tensile test, by doing compression test, by doing fatigue test. You have to calculate how much load it can withstand, how much load the material can withstand. Then only you can say that what is the fatigue limit. See, the metals which undergo strain aging have well defined. So that means if it is a loading or if it is undergoing strain aging, have well defined fatigue limits. So let me explain with the help of graph here. Please observe the graph here. Here you are seeing this is the delta y1, increase delta y1. This particular graph, this is the starting point of the graph in stress versus strain. This will grow like this. So this particular region delta y1 says that increase in stress produced by pre-strain, and the next one sigma, that is the delta y2, says increase in stress produced by aging. So that means this is produced due to pre-strain, this will produce due to the time. So that means if you keep the material for a particular period of time, so that means, or if you are keeping the same load at frequent intervals of time, automatically the sigma, that is the delta y2, will be the reason. That means increase in stress may happen in the material. and after that delta y3 means the total of delta y1 and delta y2. So this anyway this is the change here because of some pre-strain change in ultimate tensile strength due to the straining and aging. See, this is the initial graph, the dotted line, but this is the abrupt change if the pre-strain is existed. What is the difference between what is the observation that you have done by observing these two images here? Please observe these two images here. First one starts with origin and goes like this. This tensile, that is a graph, stress versus strain graph, starts from this like this. If you observe the second one, the second graph like this, what is the difference here? See, this material, whatever the graph that you have taken and whatever the material that you have taken here for this, for to generate this graph, that material is having pre-strain. If the material is having pre-strain, we can say that the graph will start like this and the some change, that is a change in ultimate tensile strength due to straining and aging. So this difference is represented as a total elongation or whatever the change that you can say that change in total elongation due to straining and aging. So that is the information with the graph, and you can observe the specimen, what are the specimen that you have taken with less amount of nitrogen and carbon. Whatever the material that you have taken, if it is having less nitrogen and the carbon, will have less tendency. Please note it down this particular point here. If the material that you have taken is having less nitrogen and carbon, will have less tendency for strain aging. So if strain aging is less, automatically we will get, and we can ensure that what is the fatigue limit and stress versus load curve, that is the SN curve, will not show the fatigue limit for this specimen. These are the some problems due to the strain aging. Suppose if you are unable to identify the fatigue limit for a material, so we cannot identify some of the properties of the material. So please observe the point here, the heat treated steels. That means heat treated means that is heat given to the material and cooling will be provided for a material. For heat treated steel show definite fatigue limit. So that means if that material, what are the material that you have taken, if it is a heat treated steel, so then we can say that it shows a fatigue limit. So if you take the example of a steel, and you can observe here, steel is having, this is a heat treated steel here, it is showing some limit here, endurance limit, at what particular point, at what stress, and the stress will be constant. On the x-axis, number of cycles, and on the y-axis stress. This is a SN curve, stress versus number of cycles. You can observe the aluminum curve here. It is not showing any endurance limit, and anyway endurance limit, because if this is not heat treated, automatically the endurance limit will decrease like this. And the number of cycles, the stress is also very less compared to steel, and here also the stress is not constant. You cannot say particular stress concentrated area and particular fatigue limit. That's the big problem. That is all about second theory, that is a fatigue limit theory. Now come to the Woods theory, what it says. See, before going to understand the Woods theory, consider this statement here. Try to understand this statement. The strain direction, whatever the strain, that means the deformation. The deformation direction here in fatigue is reversed again and again. Suppose in any material, if the strain direction, so that means if it is a deformed in the front direction and again if it is reversed. So if this particular, that is a deformation, that is the strain direction, that is due to the fatigue is reversed again and again, automatically what will happen? The slip is going to be produced, and by this type of fatigue, if the slip is produced because of this repeated, the again and again strains, automatically the crack is going to be generated. So this is all says about Wood's theory, and he says that the slip bands, which are slip movements of the order of 10 power minus 8 mm. He says about the length. This is the length, and 10 power minus 6 and 10 power minus 5 mm in height. Around this height, the slip bands may be existed. And it also says that, that is, when there is a strain in one single direction, the steps that appear are simple. Suppose if it is only in single direction, the identification of slip, identification of crack is going to be very simple. But the problem is the strain direction is not in one direction. The strain is moving in forward direction, again in backward direction, forward and backward. So that means it is going to be a repeated directions, and it is reversed in their directions, and it will be done again and again. If it is done again and again, automatically some problem may be identified in identification. So that means here when the loading is cyclic, the slip bands tend to group as notches. That means the slip bands itself, it acts as a notches, it acts as a edges. Then from those notches, the crack is going to be generated. The Wood says that due to the strain in forward and backward, the slip bands create the notches. Due to that notches, anyway I will show in terms of the figure also. What are the notch generated due to the forward direction of the slip band and the backward direction of the slip band, or the forward strain and the backward strain, the notches will be generated. The notch acts as a starting point for the fatigue cracks. So these notches are very dangerous. If you are unable to avoid, if you are unable to reduce these notches, automatically the entire material is going to get cracks. See, the notch, whatever the notch is going to generate here, are started with very small root radius. You cannot identify with the help of naked. That's the biggest problem. That's the Wood theory says. The notch will be generated. So a very small root radius acts as a stress riser. I already said that these notches are acting as a stress riser, stress concentrated areas, and the crack slowly propagates through the material. So that is going to be a biggest problem for the material. Now you can observe here. It also says that after some time the stage will come when the remaining portion of cross section is too small to bear the maximum load. It cannot, any material cannot bear the maximum load. If the strain, if the slip band is going to move in forward direction, again in backward direction, any material can't withstand. That's the problem. At this point, the failure may be observed. The final fracture is usually of a cleavage type. You can observe here. These are the slip bands in forward direction, in backward direction. So that means to and fro direction. Some bands move in forward direction, some bands move in backward direction. If this is happened, the Wood theory says that if this is happened, the crack will generate. These slip bands act as a notches or edges. Automatically, the crack is going to be generated because of these woods and these slip bands. This particular mechanism is faced by the woods, and the crack will be generated, and ultimately the fracture is going to be absorbed by the material. The next one is the dislocation movement theory. This is a very understandable and important theory which says about the failure mechanism. See, in any material, not only in a single material, if the dislocations are not restricted, I repeat it, if the dislocation is not restricted, you cannot avoid the fatigue failure or the creep failure or whatever the failures that are observed in the material. I repeat, if the dislocation movement is not restricted, you cannot avoid the cracks observed in the material. So that means what is important here? The dislocation movement must arrest. Whatever the dislocation, We cannot say that dislocations can be avoided. I repeat this particular statement, which is very important. We cannot avoid the dislocation. We can restrict the movement of the dislocation only. The next question is, what will happen if the dislocation movement is restricted? If the dislocation movement is restricted, automatically we can say that the dislocation, because of the dislocation movement restriction, the cracks can be reduced at least up to some percentage. I cannot say that up to maximum percentage the cracks can be reduced. We can say that the cracks can be reduced. Here the localized deformation will happen. So let me explain this dislocation movement theory. This deformation, whatever the deformation that is observed in the material, so these deformations are called, because of the dislocations, are called as extrusions. I repeat, these are represented as a extrusions, and means that, what do you mean by extrusions? Due to this dislocation movement, some metal is expelled out of the surface. That means this type of extrusions are represented as some metal. If any metal is expelled out of the surface, then that can be represented as the extrusion because of the dislocation movement. So please observe the image here. Here the dislocation movement, the blue color. Observe the dislocation movement here. This dislocation movement starts at this place and moves from one place to another place. How I can say that this is a dislocation? Some number of atoms are missed here. The blue color line, please observe the blue color line carefully. Some atoms are missed. This is called as a dislocation movement. Because of this, here the extrusions will happen, which are represented. Sometimes these may be inverse of extrusions, so that is represented as intrusions. Whatever the extrusions or intrusions here, we are saying that these are the responsible for the initiation of the crack. So that means whatever the extrusions that we have said, and what are the dislocation movements, if you are unable to restrict the dislocation movement in the material, we cannot say that the crack can be avoided. If you avoid the dislocation movement, if you are able to reduce the dislocation movement, automatically we can say that the crack can be reduced. Please observe here. Please observe the image here. Assume that this is the material. This is the material, and these are the slip planes. All these are slip planes here. All these are slip planes. These are the extrusions come out expelled from the metal surface, and some metals, that is some bands, that is some slip bands, are that is reversed in the reverse direction. These are called as intrusions. If it gets back to in reverse direction, these are called as intrusions. If it expelled from the surface, that is called as extrusions. So this is extrusion, this is intrusion. It may be extrusion or intrusion because of the slip planes. Automatically we can say that the particular crack, whatever the crack is going to be generated in the materials, that will generated due to extrusion and intrusion. So this is the surface, and this is about the theory behind dislocation movement. So that means here we can say that dislocation movement has to be restricted first. If you are able to dislocation, or if you are able to restrict the dislocation movement, you can avoid the extrusions or intrusions which are generated or which causes the crack initiation. So that is very important. See, in order to secure the satisfactory fatigue life, you have to take care of the modifications of the design to avoid stress concentration by eliminating sharp recesses and precise control of the surface finish. That is very important to avoid the damage that is observed on the material. Here that material, suppose if you are unable to reduce the surface finish properly, automatically that leads to crack, maybe by rough machining, maybe by punching, stamping, shearing. So you have to take care of the surface finish also, and you have to take care of the crack initiation also. to reduce stress concentration. As I said already, you have to avoid sharp corners like this. This is a poor design. This is somewhat good design compared to the previous one. If you want to provide threads, this is a poor design. This is somewhat good compared to previous one only, but this is the best design. This is a preferable design compared to this. Here you can observe the shaft and the thread axis is almost in line. You cannot, that is, you can say that the crack initiation can be reduced. I can say, and I cannot say that the crack can be avoided. Crack can be reduced. You can see here the effect of weld residual stresses. All the residual stresses, whatever the residual stresses that are generated, all those residual stresses are generated in this region. You have to take care of these residual stresses. So in initial stages, these stresses will not generate it. But in this area, the residual stresses will generate. You have to take care of all these residual stresses. See, this is the initiation of the crack. This is the propagation of the crack. And everything is, if you want to restrict the crack, you have to take care of all these theory. You have to understand all these Rong's theory, Wood's theory, fatigue limitation theory, or the dislocation movement theory, and this is the mechanism initiation. If you are able to avoid at the stage of the first one, that is the crack initiation stage, automatically we can reduce the cracks, the failure of the material, the fatigue failure of the material. So the propagation will be like this. Sometimes it depends on the material. It depends on the resistance of the material. Once the fracture will be observed. So this is the third stage of the fatigue failure. So you have to take care of the material so that the initiation, at the initiation stage itself, the cracks can be reduced. So this is all about the mechanism and theories of fatigue failure. See, I hope you have understood. So you can, if you have any doubts, you can ask me in the chat box. I'm available. So I am Kakarla Krishna Kishore, professor in mechanical engineering. So thank you one and all. So we will meet with the next topic in material technology in coming sessions. So thank you one and all.